You have lived your entire life inside time. Every moment of your existence has occurred within its flow. You have measured it, scheduled by it, waited for it to pass, wished you had more of it. You understand time the way you understand breathing. It simply happens. It moves forward. It affects everyone equally. A second is a second. An hour is an hour. A year passes the same way for everyone, everywhere. This understanding feels so fundamental that questioning it seems absurd. Time is the one thing that remains constant while everything else changes. You age, your surroundings transform, the world evolves. But time itself, the container in which all of this occurs, stays perfectly steady. It is the stage upon which reality performs. It is the river that carries everything forward at the same unchanging rate. Except it is not. Time does not flow the same way for everyone. It is not constant. It is not universal. It is not even the same for you right now as it is for someone standing a few feet away from you. The second you just experienced was not the same length as the second experienced by someone moving past you. The year that passes for you here on Earth's surface is measurably different from the year passing for someone in orbit above you. Time bends, it stretches, it compresses, it changes based on how fast you move and how deep you sit in a gravitational field. This is not philosophy. This is not metaphor. This is measured reality. We have tested it. We have proven it. We have built our most essential technologies around compensating for it. And yet it remains one of the most difficult truths about the universe to truly accept, because it contradicts every single instinct you have developed about how reality works. What you are about to explore is not a correction of a minor detail. It is a fundamental restructuring of what existence means. By the end, you will understand why there is no universal now, why your present moment is yours alone, why time is not something that happens to you, but something you move through differently than everyone else. The word time will still sound familiar, but what it actually means will have changed completely. You wake up in the morning and check the time. Your phone displays the exact hour and minute. Across the room, a clock on the wall shows the same time. In the kitchen, the microwave's digital display agrees. If you walk outside and ask a stranger what time it is, their answer will match yours within seconds. This synchronicity feels natural. It feels obvious. It is the foundation of how human civilization organizes itself. Every meeting you have ever attended began because multiple people agreed on when it would start. Every train, every flight, every broadcast, every coordinated human activity depends on the assumption that time passes identically for everyone involved. When you schedule something for 3 o'clock, you trust that 3 o'clock will arrive for you at the same moment it arrives for everyone else in your city. This trust is so deeply embedded that you have never questioned it. Clocks might break, they might run fast or slow, but time itself does not change. Time is the measuring stick that never warps. Consider what happens when you set 2 atomic clocks next to each other. These are not ordinary clocks. They do not rely on springs or gears or quartz crystals. They measure time by counting the oscillations of cesium atoms, which vibrate at a rate so consistent that a good atomic clock will not gain or lose a second in tens of millions of years. If you start 2 atomic clocks at the same moment and leave them sitting side by side on a table, they will remain synchronized almost perfectly. 1 second later, they will both show that 1 second has passed. 1 hour later, they will agree on the hour. 1 year later, the difference between them will be unmeasurable by any practical standard. This is not surprising. This is exactly what you would expect. Time passes, and both clocks measure that passage with extraordinary precision. They are not measuring different things. They are both measuring the same universal phenomenon, the forward movement of time itself. You could place 100 atomic clocks in the same room, and they would all tick in unison. You could place them in different rooms, different buildings, different cities. As long as they remain stationary on Earth's surface, they will continue to agree. The rate at which time passes does not change based on location, as long as that location is not moving relative to the others and sits at roughly the same elevation. Now extend this further. Imagine you could place atomic clocks all across the surface of the Earth. 1 in New York, 1 in London, 1 in Tokyo, 1 in Sydney, 1 at the North Pole and another at the equator. Despite the vast distances separating them, despite the different environments and climates and cultures surrounding them, they would all measure time at the same rate. A second in New York is a second in Tokyo. An hour in London equals an hour in Sydney. The planet rotates, weather changes, people move. But time remains perfectly mathematically constant across the entire surface. This constancy allows for precision on scales that would otherwise be impossible. When a television network broadcasts a live event, viewers around the world can watch it unfold at the same moment, accounting only for the finite speed at which signals travel. When scientists coordinate observations of a distant astronomical event, they can synchronize their instruments across continents and know that their measurements are capturing the same instant. The global economy runs on transactions that must be time-stamped with enough accuracy to prevent fraud and ensure fairness. Stock markets in different countries must agree on when trades occur down to the millisecond. Financial institutions transfer trillions of dollars based on timestamps that everyone trusts to be measuring the same thing. All of this works because we can agree on when things happen. We can create a shared timeline. Human civilization has spent centuries refining this synchronization. Before accurate clocks, towns set their time by the sun's position, which meant that noon in one city occurred at a slightly different moment than noon in another city 100 miles east or west. This was acceptable when travel was slow and communication took days. A letter took weeks to arrive. A journey took months. The lack of synchronized time caused no practical problems because nothing happened fast enough to require it. But as trains began connecting cities and telegraphs began transmitting messages instantly, the lack of synchronized time became a genuine obstacle. Train schedules became nightmares of conflicting local times. A train departing one city at noon would arrive in another city at a time that depended on whose clock you trusted. In the late 1800s, the world adopted time zones, dividing the planet into regions that would all agree on the hour, even if local solar noon varied slightly within each zone. This was not a scientific necessity, it was a practical convenience, but it worked because the underlying assumption held true. Time itself was universal, even if our method of labeling it was arbitrary. The zones were human inventions, but the time they measured was assumed to be a fundamental property of reality that operated the same way everywhere. No one questioned whether time in one zone actually passed at the same rate as time in another. The question did not even make sense. Time was time. It flowed forward uniformly, and all we were doing was choosing where to place the boundaries on our clocks. By the early 1900s, physicists had developed clocks accurate enough to measure time to the millisecond. By the mid-1900s, atomic clocks could measure it to the nanosecond. By the early 2000s, the best atomic clocks could detect differences smaller than a billionth of a second. These instruments represented humanity's most precise measurement tools, more accurate than any other device we have ever built. And as these clocks became more precise, something unexpected began to appear. The perfect synchronicity started to break, not because the clocks were flawed, but because time itself was not behaving the way everyone assumed it would. The first hints came from experiments that seemed almost absurdly careful. Scientists would take two atomic clocks, synchronize them perfectly, and then separate them by small distances or small changes in conditions. They would place one clock on the ground floor of a building and another on the top floor. They would keep one stationary and move another in a circle. They would fly one in an airplane while the other remained on the ground. In each case, when the clocks were brought back together and compared, they no longer agreed. One clock had measured more time passing than the other. One clock was ahead. One clock was behind. The differences were tiny, measurable only in billionths or trillionths of a second. But they were real. They were consistent. They were reproducible. At first, this seemed like it must be an error. Some subtle flaw in the experimental setup. Some environmental factor affecting the clocks. But the differences appeared in exactly the patterns predicted by equations written decades earlier. Equations that suggested something impossible, that time itself does not pass at the same rate for everyone. That motion through space affects motion through time. That gravity affects the rate at which moments accumulate. The experiments were not revealing flaws in the clocks, they were revealing properties of time that no human had ever directly observed before, because no human had ever built instruments precise enough to detect them. If you take two atomic clocks that have been sitting side by side, ticking in perfect unison, and you move one of them, something changes. Not something in the clock, something in time itself. The clock that moves begins to experience time differently than the clock that stays still. When you bring them back together and compare them, they no longer agree. The difference might be measurable only in nanoseconds, but it is absolutely real, and it reveals something profoundly unsettling about the nature of reality. Time is not a universal river carrying everything forward at the same rate. Time is more like an ocean, with currents that flow at different speeds depending on where you are and how you are moving. This changes everything. It means that the synchronicity you observe in your daily life is not evidence that time is universal. It is evidence that you and everything around you are moving through space at nearly identical speeds and sitting at nearly identical positions in Earth's gravitational field. The clocks in your house agree with each other not because they are measuring some absolute universal time, but because they are experiencing time at nearly the same rate. They are travelling through time together, like boats drifting in the same current. If you could change your motion significantly, or change your position in gravity significantly, you would drift into a different current. Time would begin to pass differently for you, not in your perception, not in your experience, but in measurable, physical reality. The perfect agreement between clocks is an illusion created by circumstance. It holds as long as everything remains nearly stationary relative to everything else, and sits at roughly the same elevation. But move fast enough, or climb high enough, and the illusion breaks. The clocks begin to disagree. Time itself begins to fracture into different rates for different observers, and once you see this, once you accept what the measurements are showing, you realize that the universe does not care about your intuition. It does not care that this seems wrong. The measurements do not lie. Time bends, and everything you thought you understood about it needs to be rebuilt from the ground up. You're sitting in a chair right now, reading these words. You feel stationary. You feel at rest. From your perspective, you are not moving. The room around you is still. The objects near you remain in place. This sense of being motionless is so convincing that it forms the baseline for how you understand movement. When you get up and walk across the room, you are moving and the room is not. When you ride in a car, you are moving and the landscape is not. Motion, in your experience, is something that happens to you while the world remains fixed. But this is not actually true. You are moving right now. You are moving quite fast. The Earth rotates on its axis, carrying you eastward at approximately 1,000 miles per hour if you are near the equator, slower if you are closer to the poles. The Earth also orbits the Sun at roughly 67,000 miles per hour. The Sun orbits the centre of the Milky Way galaxy at around 500,000 miles per hour. The galaxy itself moves through space relative to other galaxies at speeds that vary but can reach millions of miles per hour. You are in constant motion through space at extraordinary velocities. You simply do not feel it because everything around you is moving with you at the same speed. This is the key insight that makes relativity possible to understand. Motion is not absolute. It is always relative to something else. When you say you're sitting still, what you mean is that you are not moving relative to the chair, the floor, the building, or the earth beneath you, but you are absolutely moving relative to the Sun, and the Sun is moving relative to the galaxy. There is no universal reference frame, no cosmic grid against which all motion can be measured. There is only motion relative to other objects. And this relativity of motion has a consequence that seems impossible until you see the evidence. It affects how fast time passes for you. In the early 20th century, Albert Einstein proposed something that contradicted all human intuition about time. He suggested that if you move relative to someone else, time passes more slowly for you from their perspective, and time passes more slowly for them from your perspective. This is not a perceptual trick. It is not an illusion. It is a physical change in the rate at which moments accumulate. The faster you move relative to another observer, the more pronounced this effect becomes. At everyday speeds, the difference is so small that it is utterly undetectable without atomic clocks. But at speeds approaching the speed of light, the difference becomes enormous. Imagine you're standing on a train platform holding a perfectly synchronized atomic clock. A train approaches, moving at a significant fraction of the speed of light. On that train, someone else holds an identical atomic clock that was synchronized with yours before the train started moving. As the train passes you, both of you observe the other person's clock. What you see is that their clock is ticking more slowly than yours. Each second on their clock takes longer to pass than each second on your clock. From your perspective, time on the train has slowed down. But here is the strange part. From their perspective on the train, your clock is the one ticking slowly. They see your time as dilated, not theirs. Both observations are correct. Both are measuring real physical phenomena. There is no contradiction because there is no universal time to compare against. This seems logically impossible. How can both clocks be slower than the other? The resolution comes from understanding that time is not separate from space. When you move through space, you're also changing your motion through time. Space and time are woven together into a single four-dimensional fabric called space-time. Everything in the universe is always moving through space-time at the speed of light. Not through space at the speed of light, but through the combination of space and time. When you're sitting still in space, all of your motion is through time, which is why time passes normally for you. When you begin moving through space, some of your motion through space-time gets redirected from the time dimension into the space dimensions. The faster you move through space, the slower you move through time. This is not a metaphor. This is a mathematical description of reality that has been tested and confirmed thousands of times. Particles and accelerators routinely move at speeds close to the speed of light, and their behavior precisely matches the predictions of time dilation. Unstable particles that would normally decay in microseconds survive for much longer when accelerated to high speeds, not because something about the particle changes, but because time itself is passing more slowly for those particles relative to the laboratory measuring them. The particles are not experiencing anything unusual. From their own perspective, they decay in the same amount of time they always do. But from the laboratory's perspective, the particles' clocks are running slow. Consider muons, unstable subatomic particles created when cosmic rays strike the upper atmosphere. A muon at rest decays in about 2 microseconds. This is such a short lifetime that even moving at nearly the speed of light, a muon created in the upper atmosphere should only travel about 600 meters before decaying. The upper atmosphere is many kilometers above Earth's surface. By all logic, muons created there should never reach the ground. They should decay long before arriving, and yet muons reach the ground constantly. Detectors on the surface measure them all the time. This is not because muons are special. It is because they are moving so fast relative to Earth that time dilation extends their lifespan from our perspective. From the muon's perspective, it still only lives for 2 microseconds. But from Earth's perspective, those 2 microseconds stretch into much longer durations because the muon's clock is running slower than ours. This effect scales with velocity. At 10% the speed of light, time dilation is barely noticeable, slowing time by about 0.5%. At 50% the speed of light, time slows by about 15%. At 90% the speed of light, time slows by more than half. At 99% the speed of light, time passes at about 1/7 the normal rate. At 99.9%, it slows to about 1/22. As you approach the speed of light, time dilation grows without limit. At exactly the speed of light, time stops completely from an outside observer's perspective. This is why nothing with mass can reach the speed of light. It would require infinite energy to accelerate to a speed where time stops. Now bring this back down to human scales. You will never travel at 90% the speed of light. You will probably never travel at even 1% the speed of light. The fastest spacecraft humans have built move at tiny fractions of light speed. Voyager 1, the fastest human-made object to leave the solar system, travels at about 0.006% the speed of light. At that speed, time dilation is real but extraordinarily small. After travelling for decades, the clock on Voyager 1 is behind Earth clocks by less than a second, but it is behind. The difference is measurable. The effect is real. Even at the speeds you experience daily, time dilation exists. When you drive a car at highway speeds, your clock runs slower than a clock sitting still by about 1 part in a trillion. Over the course of an hour-long drive, you age less than 1/1000th of a second compared to someone who stayed home. This is not hypothetical. This is not theoretical. This is measured reality. If you could carry an atomic clock accurate enough in your car and compare it to one that stayed home, you would see the difference. The numbers are absurdly small, but they are not zero. Time is not passing at the same rate for you when you are moving. This creates a strange situation where every time you move, you're shifting slightly out of sync with the rest of the world. Every car ride, every flight, every walk down the street, you're experiencing time at a very slightly different rate than the ground beneath you. The differences are so small that they have no practical impact on your life, but they accumulate. They are real, and they point to a truth that is very difficult to internalize. There is no universal clock, There is no absolute time that everyone shares. Every object in the universe is experiencing its own rate of time based on how it is moving through space. When Einstein first published these ideas, they were met with disbelief. Not because the mathematics were wrong, but because the implications felt absurd. Time was supposed to be absolute. Clocks might malfunction, but time itself was the unchanging backdrop of existence. The idea that motion could affect time seemed to confuse the measurement with the thing being measured. But experiment after experiment confirmed the predictions. Atomic clocks flown around the world on airplanes came back measurably out of sync with clocks that stayed on the ground, with the differences matching Einstein's equations almost perfectly. Particle accelerators showed particles living longer than they should, exactly as predicted. GPS satellites had to account for time dilation, or their positioning calculations would drift by kilometers every day. The evidence became overwhelming. Time is not absolute. It is not universal. It does not flow at the same rate for everyone. It bends in response to motion. And this bending is not a minor technical detail. It is a fundamental restructuring of what it means for events to happen. When you say something happened at a specific time, you are only describing when it happened for you, in your reference frame, moving at your velocity. Someone moving at a different velocity would assign a different time to that same event. Both times are correct. Both are measuring real aspects of when the event occurred. There is no deeper truth, no absolute moment at which the event really happened. Time is personal. It belongs to the observer, and motion changes everything. You are standing on the surface of the Earth right now. Beneath your feet, the planet extends downward for thousands of miles, a sphere of rock and metal with a mass so enormous that it warps the space around it. You do not feel this warping, you feel only its consequence, weight. The sensation of gravity pulling you downward feels like a force, like an invisible hand pressing you toward the ground. For most of human history, that is exactly what people thought gravity was. A force, an attraction between masses, something that pulled objects together across empty space. But gravity is not a force. It is a curvature of space-time itself. Mass does not pull on other mass. Mass bends the fabric of space and time around it, and objects moving through that bent space-time follow curved paths. This is not just a different way of describing the same thing. It is a fundamentally different phenomenon with fundamentally different consequences. And one of those consequences is this. Gravity does not just affect how objects move through space, it affects how they move through time. The deeper you sit in a gravitational field, the slower time passes for you relative to someone farther away from the source of that gravity. This is not intuitive. Nothing in your daily experience prepares you for the idea that your elevation affects how fast you age. But it does. If you stand at sea level and your friend stands on top of a mountain, time passes more slowly for you than it does for them. You're deeper in Earth's gravitational well. The curvature of space-time around you is more pronounced. Each second you experience is slightly longer from your friend's perspective than each second they experience. The difference is incredibly small. Over the course of a full year, the person at sea level will age less than 100 millionth of a second compared to the person on the mountain. But the difference is real. It has been measured. It is not an artifact of measurement error or experimental noise. It is time itself running at different rates. Consider what this means. Right now, your head is aging faster than your feet. Your head is farther from the center of the Earth than your feet are. It sits in a slightly weaker gravitational field. Time passes more quickly there. Over the course of your entire lifetime, your head will age about 90 billionths of a second more than your feet. This is an absurdly small number. It has no biological significance. You will never notice it. But it is happening. Every moment of your life, different parts of your body are experiencing time at slightly different rates based on their distance from the planet's center. Now scale this up. The International Space Station orbits about 400 kilometers above Earth's surface. Astronauts on the station are farther from Earth's center than people on the ground. They sit in a weaker gravitational field. From the perspective of gravitational time dilation alone, time should pass faster for them than it does for people on Earth. And it does. But there is a complication. The space station is also moving very fast, orbiting Earth at about 28,000 kilometers per hour. This motion creates time dilation in the opposite direction, slowing time for the astronauts relative to people on the ground. The two effects work against each other. For the space station's specific altitude and velocity, the velocity effect is stronger. Astronauts on the ISS age slightly slower than people on Earth, but not by as much as velocity alone would predict, because the weaker gravity partially compensates. This interplay between gravitational time dilation and velocity-based time dilation is always present. Every object experiences both. When you're sitting still on Earth's surface, you're not moving much through space, but you're sitting relatively deep in Earth's gravitational field, so time passes more slowly for you than it would for someone floating in empty space far from any mass. When you move, you add velocity-based time dilation on top of the gravitational effect. The total time dilation you experience is the combination of both contributions. For most situations in everyday life, both effects are negligibly small, but they are never zero. Time is always bending, always varying, always running at slightly different rates for different observers in different circumstances. Gravitational time dilation becomes more extreme as gravity becomes stronger. On Earth, the effect is tiny because Earth's gravity is relatively weak, but move to a denser, more massive object and the effect grows. On the surface of the Sun, time passes about 66 parts per million, slower than it does in empty space far from the Sun. This is still a small effect, but it is measurable. A clock on the Sun's surface would fall behind a distant clock by about 2 seconds per year. On a white dwarf star, a collapsed stellar remnant with mass comparable to the Sun compressed into a volume the size of Earth, gravity is hundreds of thousands of times stronger than on Earth, and time dilation increases proportionally. On a neutron star, even denser still, time runs noticeably slower. A clock on the surface of a neutron star would lag behind a distant clock by a substantial fraction, perhaps 20 or 30% depending on the star's exact mass and radius. But these are still just points along a spectrum. Gravitational time dilation does not have an upper limit as long as you stay outside the event horizon of a black hole. As you approach a black hole, gravity grows stronger and time dilation grows more extreme. At a certain distance from the black hole, time passes at half the rate it does far away. Closer still, it drops to a quarter, then a tenth, then a hundredth. The closer you get, the more extreme the dilation becomes, growing without bound as you approach the event horizon. At the event horizon itself, time dilation becomes infinite. Time stops completely from the perspective of a distant observer. An object falling toward a black hole appears to slow down as it approaches the horizon, taking longer and longer to fall each successive meter, asymptotically approaching the horizon but never quite reaching it from an outside perspective. From the perspective of the falling object, nothing strange happens. It crosses the horizon in finite time. Its clock continues ticking normally. But from the perspective of someone watching from far away, the object never crosses. It just gets slower and slower, redder and redder as its light stretches to longer wavelengths, dimmer and dimmer as the photons are stretched further apart in time until it fades from view entirely. The two perspectives are both correct. Both are describing the same event. But because time itself is running at different rates in different locations, the event appears completely different depending on where you observe it from. This is not science fiction. This is observed reality. Astronomers have watched matter spiral into black holes and have seen exactly this behavior. In falling, material appears to slow down and freeze at the event horizon, glowing intensely just outside and then fading away. This is not because anything is physically stopping the material from falling. It is because time dilation has become so extreme that the final moments of infall, as measured by the infalling matter's own clock, are stretched into eternity as measured by clocks far away. The matter crosses the horizon. It continues into the black hole. But that crossing takes infinite time from an external perspective, so it is never observed to complete. Bring this back to Earth, back to elevations and buildings and mountains. The effects here are small, but they follow the same principles. A clock on the ground floor of a skyscraper runs slower than a clock on the top floor. The difference is about 100 nanoseconds per day for a typical tall building. This has been measured directly. Physicists have placed atomic clocks at different elevations in the same building and confirmed that the higher clock runs faster. They have taken clocks up mountains and measured the same effect. They have flown clocks in airplanes and satellites and measured both the gravitational and velocity contributions to time dilation, finding perfect agreement with predictions. These measurements have practical consequences. The global positioning system depends on satellites transmitting precisely timed signals to receivers on the ground. The satellites orbit at about 20,000 kilometers altitude, where gravitational time dilation causes their clocks to run faster than ground clocks by about 45 microseconds per day. But the satellites are also moving at about 14,000 kilometers per hour, which causes velocity-based time dilation to slow their clocks by about 7 microseconds per day. The net effect is that satellite clocks run about 38 microseconds per day faster than ground clocks. This might seem like a trivial difference, but GPS calculates position by measuring the time it takes for signals to travel from satellites to receivers. Light travels about 30 centimeters in a nanosecond. 38 microseconds per day would cause position errors of about 10 kilometers per day if uncorrected. GPS works only because it accounts for time dilation. The system is continuously correcting for the fact that time runs at different rates in orbit than it does on the ground. You carry this correction in your pocket every time you use your phone's navigation. Every time you check your location on a map, you are seeing the practical consequence of gravitational time dilation. The technology works because engineers understood that time is not absolute. They built the system around the fact that clocks in different gravitational fields tick at different rates. This is not theoretical physics, this is infrastructure. This is the foundation of a technology that billions of people use every day. And it works only because time genuinely does bend in response to gravity. What this means is that your position in space affects your motion through time, not just metaphorically, not just as a technical correction, but fundamentally, where you are changes when you are. If you spend your life at sea level and someone else spends their life on a high plateau, they will age slightly more than you over the course of decades. The difference will be unmeasurable in biological terms, but it will be real in physical terms. You will have experienced fewer seconds, fewer moments, less time, not because your clocks malfunctioned, but because time itself was running slower for you. Gravity is not just a force that holds you to the ground, it is a distortion of time itself, and you live inside that distortion every moment of your existence. Imagine you have a twin sibling. You are born at the same moment, in the same place, and for the first years of your lives, you age together at exactly the same rate. You celebrate the same birthdays on the same days. You accumulate the same number of seconds, minutes, hours, and years. Your lives are perfectly synchronized because you're both sitting in the same gravitational field and moving at the same velocity through space. You're traveling through time together. Now imagine that on your 20th birthday, your twin boards a spacecraft. The ship accelerates to a significant fraction of the speed of light and travels outward into space, away from Earth. It travels for what feels to your twin like 5 years. Then it turns around and travels back, taking another 5 years from their perspective. When the ship returns to Earth and your twin steps out, they are 30 years old. They have lived through 10 years of time. They have experienced 10 years of memories, 10 years of aging, 10 years of moments. But when they step out of the ship, you are not 30 years old, you're much older. Decades have passed on Earth while the ship was travelling. Your twin has returned, but they have returned to your future. This is called the twin paradox, though it is not actually a paradox. It is a straightforward consequence of time dilation. The twin who travelled was moving at high velocity relative to Earth. For them, time passed normally. Each second felt like a second. Each year felt like a year. They were not experiencing anything unusual from their own perspective. But because they were moving so fast relative to Earth, time was passing more slowly for them compared to the people who stayed behind. The faster they travelled, the more pronounced this effect became. At 90% the speed of light, their 10-year journey would correspond to about 23 years passing on Earth. At 99% the speed of light, their 10 years would stretch to about 70 years on Earth. At 99.9%, it would be more than 200 years. This seems to create a logical problem. From the perspective of the travelling twin, they were at rest in their ship, and Earth was the thing moving away and then moving back. Should Earth's clocks not be the ones running slow? Should the travelling twin not expect to return and find that less time has passed on Earth than in the ship? This is why it is called a paradox. Both twins seem to have equal claim to being the stationary observer, yet they age by different amounts. Something must break the symmetry. The resolution is acceleration. The travelling twin is not in an inertial reference frame for the entire journey. They had to accelerate to reach high speed. They had to decelerate to turn around. They had to accelerate again to return home. Each of these accelerations breaks the symmetry between the two twins. The Earthbound twin remains in an approximately inertial frame the entire time, moving at constant velocity relative to the distant stars. The travelling twin does not. The travelling twin changes velocity, and that change is absolute in a way that constant velocity is not. You cannot tell if you're moving at constant velocity without looking at something else, but you can always tell when you are accelerating. You feel it. Your body is pressed against the back of the ship during acceleration. Objects in the ship fall toward the rear wall. Acceleration is detectable from within your own reference frame without looking outside. This acceleration is what makes the travelling twins' experience different from the Earthbound twins' experience. It is what causes them to age less. When you work through the mathematics of relativity, accounting for the acceleration phases, you find that the travelling twin genuinely ages less. This is not an illusion. This is not a trick of perspective. When they reunite, the travelling twin is biologically younger. Their cells have undergone fewer divisions. Their atoms have oscillated fewer times. Less time has passed for them in every measurable physical sense. They have lived fewer moments. They have a shorter history. The universe has genuinely allowed them less time. This has been tested not with human twins, but with atomic clocks. In 1971, physicists placed atomic clocks on commercial airliners and flew them around the world, some travelling eastward and some travelling westward. When the planes returned, the clocks were compared to clocks that had remained on the ground. The flying clocks had experienced both velocity-based time dilation from the motion of the aircraft and gravitational time dilation from the change in altitude. The eastward flying clocks, which moved in the direction of Earth's rotation and thus achieved higher velocities relative to the centre of the Earth, showed less elapsed time than the ground clocks. The westward flying clocks, which moved against Earth's rotation and thus achieved lower net velocities, showed more elapsed time than the ground clocks. The differences were measured in nanoseconds, but they matched the predictions of relativity almost perfectly. The clocks aged differently because they travelled different paths through space-time. More recently, experiments have achieved even greater precision. Atomic clocks have been placed on high-altitude balloons and compared to clocks on the ground below. Optical lattice clocks, accurate to within 1 second over the age of the universe, have been raised by mere centimetres and shown measurable differences in elapsed time. You can now measure gravitational time dilation over elevation changes smaller than a person's height. If you hold one of these clocks at your feet and another at your head, they will tick at different rates. The effect is about 1 part in 10 to the power of 18, but it is real and it is measurable. Your head genuinely experiences more time than your feet over the course of your life. The twin paradox is not limited to near light speeds. It happens at any speed, just with smaller effects. If one twin spends their life travelling frequently on airplanes while the other stays home, the travelling twin will age less, though by an amount far too small to notice biologically. If one twin lives in a city at sea level and the other lives in a mountain town at high elevation, the mountain twin will age more, again by an unmeasurable biological amount but a real physical one. Every time you move, every time you change elevation, you are shifting your rate of aging relative to everyone who is not moving with you. Now imagine taking this to an extreme. Imagine you could board a spacecraft that accelerates continuously at 1 gravity, providing comfortable artificial gravity for the entire journey. You accelerate for a year, turn around, decelerate for a year, and then return the same way. From your perspective, the trip takes 4 years, but during those 4 years of your time, the ship has reached a significant fraction of the speed of light. Time dilation has become substantial. When you return to Earth, you find that not 4 years have passed, but perhaps 10 or 20 or more, depending on exactly how close to light speed the ship achieved. Your 4-year journey has carried you a decade or more into Earth's future. Extend this further. If you could somehow sustain the acceleration for longer, reaching speeds closer and closer to light speed, you could travel arbitrarily far into Earth's future while experiencing only a moderate amount of time yourself. A journey that takes you 10 years could span centuries on Earth. A journey that takes you 20 years could span millennia. You would not be travelling faster than light. You would not be violating any physical laws. You would simply be following a path through space-time where your personal time is compressed relative to the time experienced by those you left behind. You would be aging slowly while the universe ages quickly around you. This creates a profound asymmetry. The travelling twin can journey into the future of the earthbound twin, but the earthbound twin cannot journey into the future of the traveller. Time travel to the future is permitted by physics. It is simply extremely difficult and expensive, requiring accelerations to near light speeds. But time travel to the past is not permitted, at least not in any straightforward way. Once the twins separate and age differently, that difference is permanent. The younger twin cannot go back and unlive those years. The older twin cannot reverse the aging they experienced. The divergence in their ages is a fixed feature of their histories. They have travelled different paths through space-time, and those paths have different lengths measured in time. This is not a thought experiment anymore. Humans have already done this, though on tiny scales. Astronauts who have spent extended periods on the International Space Station have aged less than people on Earth by a few milliseconds over the course of months in orbit. This is a real measured effect. Cosmonaut Sergei Krikalev, who spent more than 800 days in orbit over multiple missions, has aged about 22 milliseconds less than he would have if he had stayed on Earth. He has travelled 22 milliseconds into Earth's future. This is an absurdly small amount of time, but it is not zero. He is fractionally younger than he would have been otherwise. His history contains fewer moments. The implications are strange to contemplate. If you have a twin and you want to attend their 100th birthday party, but you spend years travelling at high speeds, you might arrive to find that the party already happened decades ago. Or if they travelled and you stayed, you might die of old age before they return, still young. The relationship between your ages is no longer fixed. It depends on the paths you take through space-time, and once those paths diverge, there is no way to resynchronize. You cannot undo the aging difference. You cannot go back. Time, once spent at different rates, leaves you permanently separated in age. This is the twin paradox, not a paradox at all, but a window into the deep strangeness of time. It shows that time is not a universal river carrying everyone forward together. It is a personal experience, a path through space-time that belongs to you alone. Two people born at the same moment can age by different amounts and arrive at different points in each other's futures. The universe permits this. It has always permitted this. We simply never had the technology to notice until we built clocks accurate enough to measure it and vehicles fast enough to make the differences detectable. Time is not what you thought it was. It is flexible, it bends, and it allows twins born together to age apart. Every day, billions of people around the world use their phones to find directions. They open a map application, see a blue dot representing their location, and trust that the dot is accurate to within a few meters. They navigate to addresses they have never visited. They find restaurants in unfamiliar cities. They track their runs and bike rides. They coordinate meetups with friends using real-time location sharing. All of this works so reliably and seamlessly that it feels like magic, or at least like simple technology. You tap a screen and the phone knows where you are. It seems straightforward. But underneath that blue dot is one of the most precise technological systems ever deployed. The Global Positioning System consists of a constellation of satellites orbiting Earth, each carrying atomic clocks that keep time with extraordinary accuracy. These satellites continuously broadcast signals containing their position and the exact time according to their onboard clocks. Your phone receives these signals from multiple satellites simultaneously, measures how long each signal took to travel from the satellite to your location, and uses those travel times to calculate your position. Light travels at a fixed speed, so if you know when a signal was sent and when it was received, you can determine how far it travelled. With signals from at least 4 satellites, your phone can triangulate your position in 3 dimensions plus time. The system is elegant in concept, but it requires precision that borders on the absurd. Light travels roughly 30 centimeters in 1 nanosecond. If a satellite's clock is off by even 1 microsecond, that translates to a position error of 300 meters. If the timing error reaches 10 microseconds, your phone could place you several kilometers from your actual location. The entire system depends on every satellite maintaining nearly perfect time, synchronized with every other satellite and with clocks on the ground. Any drift, any desynchronization, any accumulating error in the satellite clocks would cause the whole system to fail within hours. And here is the problem. The satellite clocks are not synchronized with ground clocks. They cannot be. The satellites orbit at an altitude of approximately 20,000 kilometers, traveling at speeds around 14,000 kilometers per hour. At that altitude and velocity, time itself runs at a different rate than it does on Earth's surface. The satellites experience both gravitational time dilation and velocity-based time dilation, and these effects push their clocks out of sync with ground clocks by tens of microseconds every single day. If engineers did nothing to compensate for this, GPS would accumulate position errors of more than 10 kilometers per day. Within a week, the system would be completely useless. The satellites are moving fast enough that velocity-based time dilation becomes significant. According to special relativity, a moving clock runs slower than a stationary clock from the perspective of a stationary observer. The GPS satellites are moving at about 4 kilometers per second relative to the surface of the Earth. At this speed, time dilation slows the satellite clocks by about 7 microseconds per day, compared to clocks on the ground. This is the same effect that would cause a travelling twin to age less than an Earthbound twin, just at much more modest velocities. The satellites are, in effect, travelling into Earth's future very slightly, aging less than ground clocks age over the same period. But the satellites are also higher in Earth's gravitational field. They sit in weaker gravity than clocks on the surface. According to general relativity, a clock in a weaker gravitational field runs faster than a clock in a stronger field. At the orbital altitude of GPS satellites, gravitational time dilation causes their clocks to run about 45 microseconds per day faster than ground clocks. This effect works in the opposite direction from the velocity effect. Gravity wants to speed the satellite clocks up. Velocity wants to slow them down. The two effects do not cancel. Gravitational time dilation is stronger at GPS orbital altitude than velocity-based time dilation. The net result is that satellite clocks run about 38 microseconds per day faster than identical clocks on Earth's surface. This is a measured fact. It has been confirmed by experiment. It is not a theoretical prediction that might be wrong. It is observed reality that the system must account for, or it will fail. So the engineers made a choice. Before the satellites were launched, they adjusted the frequency of the atomic clocks on board. Ground-based cesium atomic clocks oscillate at exactly 9,192,631,770 cycles per second. This is the definition of a second. But the clocks placed in GPS satellites were built to oscillate at a slightly different rate, 10,229,999,995.43 cycles per second. This is a slower rate. It was chosen specifically so that when the clocks experience the combined effects of gravitational and velocity-based time dilation in orbit, they will tick at exactly the right rate to stay synchronized with ground clocks. The clocks are deliberately wrong on the ground so that they will be right in orbit. This is extraordinary when you think about it carefully. The clocks are built to malfunction. If you turned one on while it was sitting in the factory, it would run slow compared to other clocks around it. But once it reaches orbit and experiences the warped space-time of its trajectory, it ticks at exactly the correct rate. The engineers designed the clocks around the assumption that time is not absolute. They built the wrongness into the hardware because they knew that relativity would correct it. And it works. Every GPS satellite launched in the past several decades has carried clocks adjusted this way, and the system maintains synchronization accurate to within a few nanoseconds. But the corrections do not stop there. The satellites do not orbit in perfect circles at perfectly constant altitudes. Their orbits are slightly elliptical, which means their velocity and altitude change over the course of each orbit. When a satellite is at a higher point in its orbit, gravitational time dilation decreases slightly. When it is moving faster, velocity-based time dilation increases slightly. These variations cause the rate of time dilation to fluctuate. The satellite's clock does not tick at a perfectly constant rate relative to ground clocks. It speeds up and slows down throughout each orbit by small but measurable amounts. To account for this, GPS receivers on the ground apply additional corrections. They know the precise orbit of each satellite. They can calculate the satellite's altitude and velocity at any moment. From that information, they can determine exactly how much time dilation the satellite is experiencing right now, and they adjust the timing data accordingly. These corrections are recalculated continuously, every moment, for every satellite in view. The system is perpetually compensating for the fact that time runs at different rates in different parts of the satellite's orbits. This is not optional. This is not a minor refinement. If you turned off the relativistic corrections, GPS would fail immediately and catastrophically. Within 2 minutes, position errors would exceed the length of a football field. Within an hour, they would exceed several kilometers. The system would become completely unusable for any practical purpose. Navigation, surveying, aviation, shipping, telecommunications, financial transactions, power grid synchronization, scientific research, every application that depends on GPS would stop working. Not because the satellites failed, not because the clocks broke, but simply because the engineers stopped accounting for the fact that time is relative. And yet most people who use GPS have no idea this is happening. They see a blue dot on a screen. They trust it. They do not think about atomic clocks or orbital mechanics or space-time curvature. They do not need to. The system handles all of that invisibly, applying relativistic corrections thousands of times per second without the user ever knowing. Time dilation is not an exotic phenomenon reserved for physicists and astronauts. It is part of the infrastructure of modern life. You interact with it every time you use your phone to navigate. You depend on it working correctly. And it works only because engineers understood that time is not the same for everyone. Consider what this means. There is a network of satellites above your head right now, orbiting Earth every 12 hours, and they are experiencing time differently than you are. Their clocks are ticking faster than yours by a measurable amount. If you could somehow grab one of those satellites and bring it down to the surface, its clock would show more elapsed time than an identical clock that stayed on the ground the whole time. The satellite clock would be ahead. It would have aged more. It would have experienced more seconds. And this difference is not an error. It is not a malfunction. It is the natural consequence of the satellite's path through space-time. This same principle applies to every satellite in orbit. Communication satellites, weather satellites, scientific instruments, all of them experience time differently than you do on the ground. The differences are small, but they are real, and they accumulate. A satellite that spends years in orbit will have aged more than it would have if it had stayed on Earth's surface, because the gravitational time dilation effect from being farther from Earth's center outweighs the velocity-based time dilation from its orbital speed. Its internal clock, if left uncorrected, would drift ahead of ground clocks by milliseconds per week, seconds per year. For most satellites, this does not matter. They are not trying to synchronize with ground clocks to nanosecond precision, but for GPS, it matters absolutely. The system is built on the assumption that all the clocks agree, and they can only agree if they account for relativity. The engineers did not have a choice about whether to include these corrections. Relativity is not optional. It is not a theory that might be wrong. It is a description of how time actually behaves, confirmed by every GPS satellite ever launched, every day, billions of times per second, as people around the world navigate to their destinations without ever realizing that the directions they are following are calculated using equations that describe the curvature of space-time. You are using relativity right now if you have ever used GPS. You have trusted your life to it if you have ever followed navigation instructions while driving. You have depended on it working correctly, and it has worked because the people who built it understood that time is not absolute. They understood that clocks at different altitudes and velocities tick at different rates. They understood that Einstein was right, and they built that understanding into the satellites before they ever left the ground. The blue dot on your screen is not just showing you where you are in space. It is showing you the practical consequence of where you are in space-time. And it is accurate because time genuinely does run at different rates, depending on how you move and where you stand. There is a particle accelerator buried beneath the border between France and Switzerland. It is called the Large Hadron Collider, and it is the largest and most powerful machine ever built for the purpose of smashing subatomic particles together at extraordinary speeds. The device is a ring 27 kilometers in circumference, lined with thousands of superconducting magnets that guide beams of protons around the circle in opposite directions. These protons are accelerated to speeds that approach the speed of light so closely that the difference becomes almost meaningless in everyday terms. They travel at 99.99999% the speed of light. At this velocity, a proton circles the entire 27-kilometer ring more than 11,000 times per second. From the perspective of observers in the laboratory, watching instruments and recording data, These protons are moving almost as fast as anything can possibly move. But from the perspective of the protons themselves, something very different is happening. Time dilation at these extreme velocities is no longer a small correction measured in nanoseconds. It is a dramatic transformation of experienced reality. A proton moving at this speed experiences time at about 1/7,000th the rate that stationary observers experience it. For every second that passes in the laboratory, the proton experiences only about 1/10 of a millisecond. Its internal clock, if it had one, would be running 7,000 times slower than the clocks on the walls of the control room. This is not a theoretical prediction. This is measured fact. The protons in the Large Hadron Collider are not stable particles that can exist indefinitely. Under normal circumstances, free protons are stable, but the collider also accelerates other particles, some of which decay rapidly. Particles like pions and muons have known lifetimes. A pion at rest decays in about 26 nanoseconds. A muon at rest decays in about 2 microseconds. These lifetimes have been measured countless times in laboratories around the world. They are fixed properties of the particles themselves. But when these particles are accelerated to near-light speeds, they do not decay in 26 nanoseconds or 2 microseconds, as measured by laboratory clocks. They survive far longer. They circle the accelerator thousands of times before decaying. They live for milliseconds or even longer, depending on their exact velocity. The particles are not experiencing anything unusual from their own perspective. From the particle's reference frame, it decays in exactly the expected time. A pion experiences 26 nanoseconds of existence and then decays. But those 26 nanoseconds of the pion's time correspond to much longer durations in the laboratory's time, because the pion is moving so fast that time dilation stretches its lifespan from the laboratory's perspective. The particle is living its normal life, aging at its normal rate, but the laboratory is watching that life unfold in extreme slow motion. This effect is visible everywhere in particle physics. Cosmic rays strike Earth's upper atmosphere constantly, creating showers of particles that cascade downward toward the surface. Many of these particles are muons, created at altitudes of 10 or 15 kilometers above the ground. A muon at rest decays in about 2 microseconds. Even moving at the speed of light, a muon could travel only about 600 meters in that time before decaying. The upper atmosphere is far higher than that. By simple arithmetic, muons created in the upper atmosphere should never reach the ground. They should decay long before completing the journey. And yet muon detectors on the surface measure them constantly. Thousands of muons pass through every square meter of Earth's surface every second. The reason is time dilation. The muons are moving at speeds extremely close to the speed of light, typically above 99%. At these speeds, time dilation factors can reach 10 or 20 or more, depending on the exact velocity. From Earth's perspective, the muon's 2 microsecond lifetime stretches to 20 or 40 microseconds, giving it enough time to traverse the entire atmosphere and reach the ground before decaying. From the muon's perspective, it still lives for only 2 microseconds, but the distance it must travel appears much shorter due to length contraction, another consequence of relativity. Both perspectives are correct. Both describe the same physical events. The muon reaches the ground because time and space are both warped by its extreme velocity. Now consider what this means for something traveling even faster, even closer to the speed of light. Particles in cosmic rays occasionally reach velocities so extreme that their time dilation factors exceed 1,000,000. These are the highest energy particles ever detected, moving at speeds where the difference between their velocity and the speed of light is less than 1 part in a trillion. From the perspective of these particles, their journey across the galaxy might take only seconds, even though the galaxy is 100,000 light-years across. From the galaxy's perspective, the particles take 100,000 years to complete the journey. Both are true. Both are measuring the same trip through the same space-time, but the experienced duration is wildly different depending on the observer. This creates a strange situation where travel time becomes almost meaningless. If you could somehow accelerate a spacecraft to these extreme velocities, you could cross the galaxy in a human lifetime from your own perspective, even though observers in the galaxy would measure your journey as taking 100,000 years. You would not be traveling faster than light. You would simply be experiencing time so slowly compared to the rest of the galaxy that vast distances become traversable within your compressed lifespan. The galaxy would age around you while you barely aged at all. But achieving these velocities requires energy. Enormous, almost incomprehensible amounts of energy. The closer you get to the speed of light, the more energy is required to accelerate further. At 90% the speed of light, your kinetic energy is about twice your rest mass energy. At 99% it is about 7 times. At 99.9% it is about 22 times. At 99.999% it is over 200 times. The energy required grows without limit as you approach the speed of light asymptotically. You can never quite reach it. You can get arbitrarily close, but each increment closer requires exponentially more energy. The Large Hadron Collider consumes about 1.3 terawatt-hours of electricity per year to keep its proton beams circulating at near-light speeds. That is enough electricity to power a small city, and it is only accelerating protons, particles so small that a single beam contains a total mass of about a billionth of a gram. Accelerating something human-sized to the same speeds would require energy outputs beyond anything humanity can currently generate. Accelerating an entire spacecraft with crew and cargo would require energy on scales that might not even be practically accessible. The universe permits travel at near-light speeds in principle, but the energy cost makes it extraordinarily difficult in practice. Still, the universe does not care about difficulty. Particles routinely achieve these speeds naturally. Cosmic rays, accelerated by supernovae and black holes and other violent astrophysical processes, reach energies far beyond what human-built accelerators can produce. The most energetic cosmic ray ever detected, observed in 1991, and nicknamed the Oh My God particle, had an energy equivalent to a baseball travelling at about 90 kilometers per hour, all concentrated in a single subatomic particle. At that energy, the particle's time dilation factor was about 300 billion trillion. From the particle's perspective, it could have crossed the entire observable universe in a fraction of a second. These are not hypothetical scenarios, these are observed phenomena. Particles moving at these speeds exist. They pass through Earth constantly. Detectors measure them. Physicists calculate their energies and velocities and confirm that their behavior matches the predictions of relativity perfectly. Time dilation at extreme velocities is not speculative. It is not uncertain. It is part of the observed structure of reality, confirmed millions of times in particle accelerators and cosmic ray detectors around the world. What this reveals is that time is not fixed. It is profoundly flexible. A particle can experience microseconds while the universe around it experiences millennia. A traveller could, in principle, journey across the galaxy within their own lifetime, while the galaxy ages by eons. The limitation is not time. The limitation is energy. The universe allows you to compress your experience of time arbitrarily, to make yourself age slowly while everything else ages quickly, but only if you can accelerate to velocities that require more energy than is practically available. Time is negotiable. The speed of light is not, and this creates a fundamental asymmetry in the universe. You can move forward through other people's time much faster than you move through your own time. You can travel to their future, but you cannot travel to their past. You cannot reverse the direction. Once you have experienced less time than someone else, that difference is permanent. The cosmic ray particle that crossed the universe in subjective seconds cannot go back and experience those eons. The muon that reached Earth's surface in its brief lifetime cannot undo the journey. Time dilation allows you to compress your future, but it does not permit you to revisit your past. The universe moves forward, and no amount of velocity changes that fundamental direction. There are objects in the universe so dense, so massive and so gravitationally powerful that they warp space-time beyond the point where normal intuitions about physics can apply. These objects are called black holes, and they represent the most extreme gravitational environments that can exist. A black hole is not a hole in space. It is a concentration of mass so intense that the escape velocity from its surface exceeds the speed of light. Since nothing can travel faster than light, nothing that crosses a certain boundary around the black hole can ever escape. That boundary is called the event horizon. It is the point of no return. Outside the event horizon, space-time is warped, but not fundamentally broken. Objects can still orbit. Light can still escape, though it is redshifted and deflected by the intense gravity. Time still flows forward, though it flows at different rates depending on how close you are to the horizon. But at the horizon itself, something extraordinary happens. Time dilation becomes infinite. From the perspective of someone watching from far away, time at the event horizon stops completely. A clock falling toward the horizon would appear to tick slower and slower, each tick taking longer than the last, asymptotically approaching zero rate but never quite stopping, just as the clock itself never quite reaches the horizon from an outside observer's perspective. This is not an optical illusion. This is not a measurement error. This is the actual structure of space-time near a black hole. Time genuinely runs at different rates at different distances from the event horizon, and as you approach the horizon, the rate approaches zero relative to distant observers. To understand what this means, you need to think carefully about what different observers see and experience, because their perspectives diverge in ways that seem contradictory but are both completely accurate. Imagine you are in a spacecraft hovering far from a black hole, watching as a colleague in another spacecraft falls toward the event horizon. Your colleague is transmitting a signal, a regular pulse sent once per second according to their onboard clock. At first, as they begin their fall, you receive these pulses once per second as well. The signals arrive regularly. Time seems to be passing normally for them from your perspective. But as they fall closer to the event horizon, something changes. The pulses start arriving more slowly. One every 2 seconds, one every 5 seconds, one every minute. The rate keeps decreasing. The pulses are also changing in other ways. They are redshifting, shifting to longer wavelengths as the photons climb out of the deepening gravitational well. A visible light pulse becomes infrared, then microwave, then radio. The signal grows dimmer as well because the photons are being stretched further apart in time. Fewer photons reach you per second. The brightness drops. Eventually the pulses arrive so slowly and are so dim and so red-shifted that you can no longer detect them. Your colleague appears to fade from view, frozen just above the event horizon, their last transmitted signal stretched out over infinite time. From your perspective, your colleague never crosses the horizon. They fall closer and closer, slowing down asymptotically, but the final moment of crossing never arrives. You could wait billions of years and you would never see them actually pass through. The event of crossing the horizon is infinitely far in your future. Your colleague appears to be frozen in time, suspended just outside the boundary, glowing faintly with radiation that is red-shifted almost to nothing. But from your colleague's perspective, something entirely different happens. They do not slow down, they do not stop, they do not hover near the horizon, they cross it in finite time according to their own clock. The pulses they transmit continue at 1-second intervals from their perspective. Their clock keeps ticking normally. They see nothing unusual at the moment they cross the event horizon. There is no barrier, no wall, no sudden change. For a sufficiently large black hole, the gravitational gradient at the horizon is gentle enough that tidal forces are negligible. They simply pass through and continue falling inward. Both perspectives are correct. From the outside, the crossing takes infinite time. From the inside, it takes finite time. There is no contradiction because the two observers are not measuring time with synchronized clocks anymore. They are so deep in different parts of the curved space-time around the black hole that their definitions of simultaneous events no longer align. What is now for the outside observer is not now for the infalling observer. The event horizon represents a boundary where these definitions diverge completely. This has profound implications. It means that from the outside perspective, nothing ever actually enters a black hole. Everything that falls toward a black hole appears to freeze at the horizon, piling up in a thin shell just outside, never quite crossing. And yet from the perspective of infalling matter, crossing happens all the time. Material falls through, continues inward, and reaches the singularity at the center in finite proper time. Both descriptions are valid in their respective reference frames. Now consider the singularity itself. At the very center of a black hole, general relativity predicts that space-time curvature becomes infinite. All the mass of the black hole is concentrated at a point of zero volume and infinite density. This is called a singularity, and it is a place where the equations of general relativity break down. The theory predicts its own failure. Physicists expect that a more complete theory, one that successfully merges general relativity with quantum mechanics, would describe what actually happens at the singularity. But no such theory currently exists. The singularity remains a mystery, a boundary of human understanding. But even without understanding the singularity itself, the event horizon has measurable effects on the universe outside. Black holes are not invisible. They reveal themselves through their gravitational influence on surrounding matter. Gas and dust falling toward a black hole form an accretion disk, a swirling disk of material that heats up through friction as it spirals inward. This material can reach temperatures of millions of degrees, hot enough to emit X-rays that can be detected across intergalactic distances. Telescopes have observed thousands of black holes this way, seeing the brilliant glow of doom material in its final moments before crossing the horizon. From the perspective of that infalling material, the journey from the outer edge of the accretion disk to the event horizon takes a measurable amount of time. The material spirals inward over days or weeks or months, heating up, emitting radiation, and eventually crossing the horizon and disappearing from view. But from the perspective of a distant observer, the material never quite reaches the horizon. It piles up, red-shifted and dimmed, frozen at the boundary. The paradox is that both descriptions are observationally accurate. Astronomers see material glowing brightly and then fading, which matches the outside perspective. But the material itself experiences a finite journey ending in crossing, which matches the infalling perspective. Stellar mass black holes formed from the collapse of massive stars have event horizons only a few kilometers across. Supermassive black holes found at the centers of galaxies can have event horizons millions of kilometers across. The black hole at the center of our Milky Way galaxy, called Sagittarius A star, has a mass about 4 million times the mass of the Sun, and an event horizon roughly 17 times the diameter of the Sun. Despite its enormous mass, the event horizon is still a tiny region compared to the scale of the galaxy itself. But within that region, time dilation effects are so extreme that they dominate the behavior of everything nearby. Stars orbit Sagittarius, a star at speeds reaching several percent of the speed of light. At those speeds, time dilation becomes measurable even without getting close to the event horizon. A star in a close orbit around the black hole experiences time more slowly than a star farther away, both because of its velocity and because of the stronger gravitational field it moves through. Astronomers have tracked these orbits for decades, watching stars complete full orbits in as little as 16 years. The orbits match the predictions of general relativity with extraordinary precision. The observations confirm that space-time around the black hole is curved exactly as Einstein's equations predict. In 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole's event horizon. The image showed a dark central region surrounded by a bright ring of emission from the accretion disk. The dark region is not the event horizon itself, which is too small to resolve, but the shadow it casts on the glowing material behind it. The image confirmed the size and shape of the shadow matched predictions. It was visual proof that black holes exist, that event horizons are real, and that the extreme space-time curvature they create is not theoretical abstraction, but observable reality. What this means is that black holes are not just exotic objects at the far edges of the universe. They are common. They exist in every galaxy. They shape the structure and evolution of those galaxies, and they represent places where time itself behaves in ways that are completely unlike anything in normal experience. Near a black hole, time is not a gentle slope where small differences accumulate slowly. It is a cliff where differences become infinite across finite distances. You can hover just outside the event horizon and watch the universe age by billions of years while you experience only moments. You can fall through the horizon and experience time normally while the outside universe never sees you cross. Time becomes observer-dependent in the most extreme way possible. This is the edge of what relativity allows. This is where time dilation reaches its ultimate limit. Beyond the event horizon lies a region where time and space exchange roles, where all paths lead inevitably to the singularity, where escape is not difficult but impossible. The event horizon is the boundary beyond which time ceases to mean what it means anywhere else. And it exists. It is real. It is out there. And it proves that time is not just flexible, it is breakable. You are sitting somewhere right now reading these words. You have a sense of the present moment. You know what is happening right now in your immediate surroundings. You can see the room around you, hear the sounds nearby, feel the air on your skin. All of this feels simultaneous. It all feels like it is happening at the same time, in the same present moment. This is your now. It is the collection of all events that you experience as occurring simultaneously. It seems like an objective fact about the universe, a shared present that everyone experiences together. But it is not shared. Your now is not the same as anyone else's now. It is unique to you, defined by your position in space and your velocity through it. Someone standing next to you has nearly the same now as you do, because they are moving at nearly the same velocity and sitting at nearly the same depth in the gravitational field. The difference between your present moments is so small that it's completely undetectable without atomic clocks. But someone far away or moving at a different velocity has a different now. Their present moment does not coincide with yours. Events that are simultaneous for you are not simultaneous for them. This is one of the strangest consequences of relativity, and it is also one of the hardest to truly internalize. Simultaneity is not absolute, it is relative. Two events that happen at the same time, according to one observer, happen at different times, according to another observer moving at a different velocity. There is no universal present moment that spans the entire universe. There is no cosmic now that everyone shares. There are only local presents, personal nows, each belonging to an observer in a particular state of motion. Consider two events happening far apart in space. A star explodes in a distant galaxy at the same moment that you snap your fingers, according to your reference frame. From your perspective, these two events are simultaneous. They both happen in your present moment. But someone travelling past you at high velocity would not agree. From their perspective, the star might have exploded years before you snapped your fingers, or years after, depending on the direction they are moving. Both observers are correct. Both are measuring time accurately in their own reference frames. But they disagree fundamentally about the order of events. This disagreement only occurs for events that are separated by enough distance that light cannot travel between them in the time interval between the events. These are called space-like separated events. For such events, different observers can disagree about which event happened first, or whether they happened simultaneously without creating any logical contradictions. The reason there is no contradiction is that the two events cannot influence each other. No signal, no information, no causal effect can travel from one event to the other if they are space-like separated. So the order in which they occur does not affect anything observable. The universe remains consistent even though different observers assign different times to the events. But for events that are close enough in space and time that light could travel from one to the other, all observers agree on the order. These are called time-like separated or light-like separated events. If one event causes another, if information travels from one to the other, then every observer in the universe will agree that the cause happened before the effect. Relativity does not permit observers to disagree about causality. It does not allow you to see effects before causes. The structure of space-time is arranged precisely to prevent such contradictions. You can disagree about simultaneity, but you cannot disagree about causal order. This creates a strange situation where the universe does not have a universal present, but it does have a universal past and future. Events in your past light cone, the region of space-time from which light could have reached you by now, are unambiguously in your past. All observers agree that those events happened before your present moment. Events in your future light cone, the region of space-time that you could influence by sending light signals, are unambiguously in your future. All observers agree that those events happen after your present moment. But events outside both light cones, events that are too far away for light to have travelled between them and you, occupy a strange middle ground. They are neither definitively in your past nor definitively in your future. Different observers assign them to different times. Now extend this to the scale of the universe. The observable universe is about 93 billion light-years across. It contains billions of galaxies, each with billions of stars. At any given moment, according to your reference frame, all of these galaxies exist simultaneously. You can define a cosmic now that includes one particular moment in the history of each galaxy. But someone in another galaxy, moving at a different velocity relative to you, would define a different cosmic now. Their present moment would slice through the history of the universe at a different angle. Events that you consider to be happening right now, they might consider to have happened millions of years ago, or millions of years in the future, depending on their motion. This means that when you look at a distant galaxy, you're not seeing what is happening there now. You're seeing what happened there in the past, because light takes time to travel from the galaxy to your eyes. The galaxy you see might be 10 million light years away, which means the light you're seeing left that galaxy 10 million years ago. You are seeing the galaxy as it was 10 million years in the past, according to your reference frame. But what is happening in that galaxy right now, according to your definition of simultaneity, is not something you can observe. It is separated from you by too much space. The information about it has not reached you yet and will not reach you for 10 million years. And here is the deeper strangeness. Someone in that distant galaxy, looking back at you right now, is seeing your galaxy as it was 10 million years ago. They are seeing Earth before humans existed, before modern mammals evolved, before much of the current geography of the planet took shape. From their perspective, the Earth you're standing on right now does not exist yet in their observable universe. It is in their future, and yet from your perspective, their current moment is also in your future. Both of you are looking at each other's past while experiencing your own presence, and neither of you can access the other's now. This creates a profound isolation. Every observer in the universe is locked into their own present moment, surrounded by their own light cone, able to observe only the past of distant objects, and able to influence only the future. The present moments of distant observers are inaccessible, hidden beyond the horizon of light travel time. You cannot know what is happening right now on the other side of the galaxy. You cannot even define what right now means there in a way that all observers would agree on. Your now is local. It is personal. It extends only as far as the region where light travel times are negligible, and where your definition of simultaneity approximately matches that of nearby observers. This is not a limitation of technology or measurement. This is a fundamental feature of space-time. The universe is structured such that no observer can have complete information about the present state of the entire universe. You can know your own present. You can know the past of distant regions. You can predict the future based on physical laws. But you cannot access the present of anywhere far from you. The present is fragmented across the universe, divided into countless local nows that do not align, that cannot be synchronized, that belong to individual observers traveling their individual paths through space-time, and yet causality is preserved. Even though you cannot agree with a distant observer about what is happening now, you can agree about what happened in the past and what will happen in the future for any events that are causally connected. If you send a light signal to that distant galaxy, all observers will agree that you sent it before it arrived. If someone in that galaxy sends a signal back, all observers will agree on the order of transmission and reception. The causal structure of the universe remains consistent. Information flows forward in time, causes precede effects. The disagreement about simultaneity does not break the logic of the universe. It simply reveals that the logic is more subtle than human intuition expects. What this means is that the universe does not have a single objective timeline. It has a network of overlapping, observer-dependent timelines, each one valid in its own reference frame, each one describing the same events but assigning them different coordinates in time. Your timeline is real. Someone else's timeline is equally real. They do not contradict each other because they are measuring different things. They are slicing through the four-dimensional structure of space-time at different angles. Both slices are valid. Both are equally true descriptions of reality. But they are not the same slice. They do not align, and there is no way to make them align without arbitrarily choosing one observer's reference frame as more fundamental than another's, which the universe does not do. All reference frames are equally valid, all presents are equally real, and none of them are universal. The fact that time runs at different rates for different observers, that simultaneity is relative, and that the present moment is not universal, raises an obvious question. Can you use time dilation to travel backward in time? If you can slow your clock relative to someone else's, if you can experience less time while they experience more, does that create a path to the past? Can you manipulate your motion through space-time in such a way that you arrive at an earlier moment before you departed? The answer, according to everything we understand about physics, is no. Time dilation allows you to reach someone else's future while experiencing less time yourself, but it does not permit you to reach their past. The universe appears to have built-in protections against backward time travel, mechanisms embedded in the structure of space-time itself that prevent paradoxes and preserve causality. Causality is the principle that causes must precede their effects. If you drop a glass, it falls and then it shatters. The falling causes the shattering. The shattering does not cause the falling. This ordering feels so fundamental that it is difficult to imagine it being violated. And yet if backward time travel were possible, causality could be violated easily. You could travel to the past and prevent the event that caused you to travel in the first place. You could create paradoxes where effects exist without causes, or where causes are erased by their own effects. These logical contradictions suggest that either backward time travel is impossible, or the universe has some mechanism to prevent paradoxes even if time travel occurs. General relativity, the theory that describes gravity and space-time curvature, does permit some solutions that contain closed time-like curves. These are paths through space-time that loop back on themselves, allowing an object to travel forward in time continuously, and yet arrive back at an earlier moment in its own history. The mathematics allows this in certain highly symmetric or exotic space-time geometries. Rotating black holes, infinitely long rotating cylinders, wormholes connecting distant regions of space-time. All of these theoretical structures can contain closed time-like curves under certain conditions. But every one of these solutions requires conditions that are either physically unrealistic or that may be prevented by quantum effects we do not yet fully understand. Consider the rotating black hole, also called a Kerr black hole. Unlike a non-rotating black hole, which has a single event horizon, a rotating black hole has two horizons and a region between them called the ergosphere. Within the ergosphere, space-time itself is dragged around the black hole by its rotation. An object in the ergosphere cannot remain stationary relative to distant stars. It must rotate with the black hole carried along by the twisting of space-time. Deeper inside, past the inner horizon, the mathematics of general relativity predicts closed time-like curves. An object could, in principle, follow a path that loops back to an earlier time, but there are problems. First, reaching the region with closed time-like curves requires crossing both horizons, falling into the black hole, and entering a region where space-time is so wildly distorted that the equations may not accurately describe reality. Second, even if you could survive the journey and navigate a closed time-like curve, you would be trapped inside the black hole. You could not escape to inform the outside universe of your time travel. You could only loop within the interior, isolated from the rest of space-time. Third, and most fundamentally, quantum effects might prevent closed time-like curves from forming at all. When physicists try to analyze what happens to quantum fields near closed time-like curves, they find that fluctuations grow without bound, potentially creating infinite energy densities that would destroy the curve before it could form. This is not proven, but it suggests that nature may have mechanisms to prevent time travel even when general relativity appears to allow it. Wormholes present similar issues. A wormhole is a hypothetical tunnel through space-time connecting two distant regions. If you could create a wormhole and then move one end of it at high velocity, while keeping the other end stationary, time dilation would cause the two ends to age at different rates. Eventually, one end of the wormhole would be in the past relative to the other end. You could enter one end and emerge from the other at an earlier time. This sounds like a viable method for backward time travel, but it requires several things that may be impossible. First, you need to create the wormhole, which requires exotic matter with negative energy density. No such matter has ever been observed, and it may not exist. Second, you need to stabilize the wormhole to prevent it from collapsing. Third, even if you overcome those obstacles, the same quantum instability that plagues closed time-like curves would likely destroy the wormhole the moment it became capable of time travel. The universe seems to resist backward time travel at every turn. Whenever a solution to the equations permits it, additional considerations, quantum effects, energy requirements, stability issues, appear to block it. This has led some physicists to propose what is called the chronology protection conjecture. This is the idea that the laws of physics contain some fundamental principle that prevents closed time-like curves from forming in any realistic scenario. The conjecture is not proven, and there is no known law of physics that explicitly forbids time travel. But the accumulation of obstacles suggests that nature does not permit it, even if the mathematics occasionally allows it. What the universe does permit is forward time travel. You can experience less time than someone else by moving at high velocity or by sitting deep in a gravitational field. You can effectively skip forward through their timeline, arriving in their future while aging less yourself. This is not speculation. This is observed reality. Astronauts do it. Particles in accelerators do it. GPS satellites compensate for it. Forward time travel is a routine, mundane, well-understood phenomenon, but there is no known mechanism to reverse it. Once you have experienced less time than someone else, you cannot go back and unexperience it. The asymmetry is built into the structure of space-time itself. This asymmetry is related to the second law of thermodynamics, which states that entropy, the measure of disorder in a system, always increases over time. This gives time a direction. The past is the direction of lower entropy. The future is the direction of higher entropy. You can unbreak an egg by carefully reversing the motion of every particle involved. In principle, but in practice, the probability of this happening spontaneously is so low that it never occurs. Time has an arrow. It points forward. And while relativity allows clocks to tick at different rates, it does not allow them to tick backward. Causality is preserved because the speed of light acts as a cosmic speed limit. No information can travel faster than light. This means that causes and effects are always separated by time-like or light-like intervals, never space-like intervals. The cause must be in the past light cone of the effect. The effect must be in the future light cone of the cause. All observers, regardless of their motion, agree on this ordering. They might disagree about how much time separates the cause and effect, but they never disagree about which came first. This structure prevents paradoxes. It ensures that the universe remains logically consistent even though different observers experience time differently. Consider what would happen if faster-than-light travel were possible. Suppose you could send a signal faster than light from Earth to a distant star. In your reference frame, the signal travels forward in time. But in the reference frame of an observer moving at high velocity relative to you, the signal might appear to travel backward in time due to the relativity of simultaneity. If that observer then sends a faster-than-light signal back to Earth, it could arrive before you sent the original signal, creating a causal loop. You could receive a reply before you sent the message. This is not just strange, it is logically contradictory. It violates causality. The fact that faster-than-light travel would permit such paradoxes is one of the reasons physicists believe it is impossible. The universe does not allow it because allowing it would break the causal structure that makes reality coherent. Time dilation does not create these problems because it does not involve faster-than-light travel. It involves moving through space-time at different rates, but always forward, always within the constraints of the light speed limit. You can age slowly while others age quickly, but you cannot reverse your aging. You can reach their future, but not their past. The asymmetry is absolute, and it preserves causality perfectly. Every event you experience has causes in your past and effects in your future. The chain of causality is never broken, never reversed, never looped back on itself. This is why the universe feels logically consistent even though time is relative. The relativity of time does not lead to paradoxes because it operates within strict boundaries. Those boundaries are the speed of light, the structure of light cones, and the forward direction of entropy increase. Within those boundaries, time can stretch and compress and vary from observer to observer without breaking the fundamental rule that causes precede effects. The universe allows extraordinary flexibility in how time is experienced, but it does not allow that flexibility to undermine the logic of cause and effect. Time is relative, but causality is absolute. You experience time passing right now. You are aware of the present moment, distinct from the past moments you remember and the future moments you anticipate. This experience feels immediate and continuous. It feels like time is flowing, like you're moving through it or it is moving through you, carrying you forward from past to future at a steady, unchanging rate. This sensation is so fundamental to consciousness that it seems inseparable from existence itself. To be aware is to be aware of time passing. To think is to experience thoughts unfolding in sequence. To perceive is to notice change, and change requires time. But this experience of time, this subjective flow that feels so real, is constructed by your brain. It is not a direct perception of physical time in the way that your eyes directly perceive photons or your ears directly perceive sound waves. There is no sensory organ for time. There is no receptor in your body that detects the passage of moments. Instead, your brain creates the sensation of time passing by, integrating information from multiple sources. Memory, sensory input, neural processing rates, and internal rhythms. What you experience as now is actually a synthesis of events that occurred over a window of roughly a few hundred milliseconds, stitched together into a single perceived moment. This window is called the specious present, and it represents the duration over which your brain integrates sensory information into a unified conscious experience. When you watch someone speak, you perceive their words and lip movements as synchronized, as happening at the same time, but the light from their lips reaches your eyes faster than the sound of their voice reaches your ears, because light travels faster than sound. Your brain compensates for this difference, delaying the visual information slightly so that it aligns with the auditory information. The result is that you perceive a coherent, synchronized event even though the sensory signals arrived at different times. Your now is not instantaneous. It is a short interval during which your brain waits for information to arrive and then assembles it into a coherent moment. This constructed nature of time perception means that your subjective experience of duration can differ from physical duration. You have experienced this countless times. When you're engaged in an absorbing activity, hours can feel like minutes. When you're bored or waiting, minutes can feel like hours. When you're in danger, time seems to slow down. You perceive more detail, more frames of experience per second, as your brain shifts into a heightened state of attention. But when you remember these moments later, you find that they occupy the same physical duration as any other moments. The feeling of time slowing was a perceptual phenomenon, not a physical one. Your brain was processing information faster, creating a denser memory, but the clock on the wall kept ticking at the same rate. The brain's construction of time is influenced by attention, emotion, novelty, and routine. Novel experiences feel longer in the moment and occupy more space in memory because your brain is processing more information, encoding more details. Routine experiences feel shorter and compress in memory because your brain filters out redundant information. This is why childhood feels long when you're living it and short when you remember it. As a child, everything is novel. Every day contains new experiences, new learning, new encoding. As an adult, routines dominate. Days blend together, weeks vanish, years accelerate. The physical time is the same, but the subjective experience changes because the brain is encoding fewer distinct memories per unit of physical time. This subjective variability in time perception is entirely separate from the physical variability of time described by relativity. Relativity says that time genuinely passes at different rates for different observers depending on their motion and position in a gravitational field. These differences are measurable with clocks. They're objective features of space-time. But human time perception varies for completely different reasons having to do with neural processing and cognitive psychology, not with space-time geometry. When time feels slow because you are bored, your clock still ticks at the normal rate. When time feels fast because you are engaged, your clock still ticks at the normal rate. The subjective feeling and the physical measurement do not align. And yet both are real. The physical passage of time, measured by atomic clocks and described by relativity, is real. The subjective experience of time, constructed by your brain and varying with your mental state, is also real. They are describing different aspects of the same phenomenon. One is a property of the external universe, the other is a property of your internal consciousness. Neither is more true than the other. They simply operate on different levels of description. Now consider that your brain constructs not just the feeling of time passing, but also the feeling of a unified present moment. When you look around a room, you perceive everything in the room as existing simultaneously in the same moment. The objects, the light, the sounds, all feel like they are present together right now. But this simultaneity is an illusion created by your brain's integration of sensory information over the specious present. The light from the far wall took slightly longer to reach your eyes than the light from a nearby object. The sound from across the room took longer to reach your ears than the sound from right next to you. Your brain compensates for these differences, creating the illusion that everything is happening at the same time. But the signals arrived at different times, and they originated at different times. Your unified present is a construction, not a direct perception. This becomes more pronounced when you consider larger distances. When you look at the moon, you're seeing it as it was about 1.25 seconds ago, because that is how long it takes light to travel from the moon to your eyes. When you look at the sun, you are seeing it as it was about 8 minutes ago. When you look at the nearest star beyond the sun, you are seeing it as it was about 4 years ago. When you look at a distant galaxy, you might be seeing it as it was billions of years ago. None of these objects exist in your actual present moment. They all exist in your past, separated from you by the light travel time. And yet when you perceive them, your brain integrates them into a single scene, a single perceptual now, as if they were all present simultaneously. The universe does not have a universal present, but your brain constructs one anyway, because it is useful for navigating the world. On human scales, light travel times are negligible. The delay between an event happening and you perceiving it is so small that treating everything as simultaneous works perfectly well. Your brain evolved to navigate a world where distances are measured in meters and kilometers, where light travel times are measured in nanoseconds and microseconds, where simultaneity is a good enough approximation of reality to be useful. Your perceptual systems are not designed to handle the relativistic realities of high velocities and vast distances. They are designed to help you catch prey, avoid predators, and interact with other humans. For those purposes, assuming a universal present works fine, but it is still an assumption. It is a useful fiction constructed by your brain to make sense of sensory input. The real structure of space-time does not support the idea of a universal present. The real structure is more complex, more fragmented, more observer-dependent, and yet you do not perceive this complexity. You perceive a simple, unified flow of time carrying you forward through a shared present. This perception is so compelling that it took thousands of years of human civilization and the genius of Einstein to realize that it was not an accurate description of physical reality. What this means is that your intuition about time is not trustworthy. Your brain is showing you a simplified, constructed version of time that works well for everyday life, but does not reflect the deeper truth. The feeling that time flows at the same rate for everyone is wrong. The feeling that there is a universal present moment is wrong. The feeling that simultaneity is absolute is wrong. These feelings are artifacts of how your brain processes information, not accurate representations of space-time. To understand time as it actually is, you have to set aside your direct perceptual experience and trust the mathematics and the measurements. You have to accept that clocks are better guides to the nature of time than your own consciousness. This is deeply counterintuitive. You are being asked to believe that something you experience constantly and intimately, something that forms the basis of your moment-to-moment awareness, is not what it seems. You are being asked to trust abstract equations and experimental results over your own lived experience, and yet the evidence is overwhelming. Atomic clocks at different elevations tick at different rates. Particles moving at high speeds live longer than stationary particles. GPS satellites require relativistic corrections to function. The universe does not care about your intuition. It operates according to principles that your brain was not designed to comprehend directly. And still, your perception is valuable. It is what allows you to exist as a conscious being navigating the world. The fact that it is a construction does not make it false. It is a useful model, accurate enough for the context in which it evolved. You do not need to perceive relativistic time dilation to live your life. You do not need to account for the relativity of simultaneity to have a conversation with someone standing next to you. Your brain's simplified model of time is good enough for nearly everything you will ever do. It is only when you step outside the narrow range of velocities and distances where human experience has been confined that the model breaks down and the deeper reality becomes visible. Your perception is not wrong, it is just incomplete, and recognizing its incompleteness is the first step toward understanding what time actually is. The nearest star to our Sun is called Proxima Centauri. It is a small red dwarf located approximately 4.2 light-years away. This means that light, travelling at 300,000 kilometers per second, takes 4.2 years to cross the distance between Proxima Centauri and Earth. If you look at that star through a telescope tonight, you are seeing photons that left its surface 4.2 years ago. You are seeing the star as it was in the past. And someone on a planet orbiting Proxima Centauri, looking back at our Sun right now, would be seeing our Sun as it was 4.2 years ago. The two stars exist in each other's observable pasts, separated by the finite speed of light. This creates an unusual situation when you try to define what is happening right now at Proxima Centauri. From your reference frame on Earth, if you are at rest relative to the Sun, You can define a moment right now at Proxima Centauri by extending your present moment across space. You imagine a slice through space-time that includes your current instant on Earth and a corresponding instant at Proxima Centauri. This slice represents all events that you consider to be simultaneous with your present, but the moment you have selected is not something you can observe. The light from that moment will not reach Earth for another 4.2 years. You are defining it based on your reference frame, your sense of simultaneity, your particular way of slicing through space-time. Now imagine someone travelling from Earth toward Proxima Centauri at high velocity. They are moving at, say, 90% the speed of light. From their reference frame, simultaneity is different. Their present moment slices through space-time at a different angle than yours. Events that you consider to be happening right now at Proxima Centauri, they consider to have already happened years ago. Events that they consider to be happening right now at Proxima Centauri, you would consider to be years in the future. Both of you are correct within your respective reference frames, but you fundamentally disagree about what moment at Proxima Centauri corresponds to your present moment on Earth. This disagreement grows larger as the distance increases. For nearby objects, moving at everyday velocities, the disagreement about simultaneity is negligible. You and someone walking past you on the street will disagree about what is happening right now on the other side of the planet by only a few nanoseconds. The difference is real, but it is so small that it has no practical meaning. But for distant objects, the disagreement becomes substantial. At interstellar distances, observers moving at different velocities can disagree about simultaneity by years or decades. At intergalactic distances, the disagreement can reach millions of years. Consider two galaxies separated by 10 million light-years. An observer at rest in one galaxy can define a present moment that includes a particular instant in the other galaxy. But an observer moving at high velocity relative to the first observer would define a different present moment, one that might be a million years earlier or later in the history of the distant galaxy, depending on the direction and speed of their motion. Both presents are equally valid. Both are correct descriptions of simultaneity in their respective reference frames. But they have almost nothing in common. The distant galaxy exists in wildly different states in the two presents. Stars that exist in one present might not have formed yet in the other. Stars that have died in one present might still be burning in the other. This means that at cosmological distances, the concept of now becomes almost meaningless. You cannot point to a distant galaxy and say what is happening there right now in any objective sense. You can only say what is happening there right now according to your particular reference frame and your particular state of motion. Change your velocity, and you change which moment in that galaxy's history corresponds to your present. The galaxy has not changed. The light travelling from it has not changed, but your definition of simultaneity has changed, and that shifts which slice of the galaxy's history you consider to be contemporaneous with your own moment. This creates profound isolation on cosmic scales. When you look at a galaxy 10 million light-years away, you see it as it was 10 million years ago. What it looks like now, according to your reference frame, is something you will not see for another 10 million years, and by the time you see it, it will be information about a moment that is now 20 million years in your past. You can never observe the present of a distant object. You can only observe its past. And the farther away the object is, the deeper into its past you're looking. The observable universe is a museum of history, displaying the past states of billions of galaxies, with the most distant objects showing you the universe as it was more than 13 billion years ago. And yet observers in those distant galaxies are experiencing their own presence right now. They have their own nows that do not align with yours. They are looking back at the Milky Way and seeing it as it was billions of years ago, just as you are looking at them and seeing them as they were billions of years ago. Everyone in the universe is observing everyone else's past while experiencing their own present, and there is no way to synchronize these presents across cosmic distances. The speed of light imposes a fundamental limit on how quickly information can travel, and this limit prevents any kind of universal simultaneity from being established or even defined in a meaningful way. Now consider what happens if you try to communicate with someone in a distant galaxy. You send a light signal. It travels at the speed of a light, taking 10 million years to cross the distance. During those 10 million years, you continue aging, experiencing time, living your life. The galaxy continues evolving. Stars form and die. Civilizations might rise and fall. When your signal finally arrives, it reaches a galaxy that has aged by 10 million years since you sent it. If they send a reply immediately, it takes another 10 million years to return to you. By the time you receive the reply, 20 million years have passed since you sent the original message. The conversation is possible in principle, but it is stretched across timescales that dwarf human lifetimes, that dwarf the entire history of human civilization. This is not a technological limitation. This is a fundamental feature of space-time. You cannot communicate faster than light. You cannot synchronize clocks across vast distances without accounting for light travel time and relativistic effects. You cannot establish a shared present with a distant observer. The isolation is built into the structure of the universe. Every observer is confined to their own light cone, able to influence only the future, able to observe only the past, unable to access the present of anywhere distant. And this isolation is not symmetric. The disagreement about simultaneity means that different observers slice through space-time differently, assigning different times to distant events. Two observers moving at different velocities will construct different maps of when things happened across the universe. Both maps are correct, both are valid, but they do not agree, and there is no way to determine which one is really correct, because there is no absolute simultaneity to compare them against. Simultaneity is observer-dependent, just like time dilation is observer-dependent. The universe does not provide a privileged reference frame. It does not tell you which way of slicing space-time is the right way. All ways are equally valid. What this means is that the universe is not just large in space, it is fragmented in time. Every observer experiences their own timeline, their own present, their own assignment of when distant events occur. These timelines overlap for nearby observers moving at similar velocities, creating the illusion of a shared present on human scales. But they diverge for distant observers or observers in relative motion, revealing that the shared present was always an approximation, a simplification that works well locally but breaks down globally. The universe does not have a single history unfolding in a single timeline. It has countless histories, countless timelines, all woven together into the four-dimensional fabric of space-time, all equally real, all equally valid, none of them universal. This is the true meaning of relativity, not just that time can be measured differently by different observers, but the time is fundamentally observer-dependent at the deepest level. There is no objective universal time. There is only the network of local times, personal times, reference frame-dependent times, each one describing the universe from a particular perspective. And at interstellar and intergalactic distances, these perspectives diverge so drastically that they become almost incomparable. The universe is vast, not just in spatial extent, but in temporal fragmentation, and every observer navigates this fragmented cosmos alone, seeing the past of distant places, experiencing their own present, unable to share that present with anyone far away. You exist in a specific location in space, at a specific moment in time. Right now, as you read these words, you occupy a particular point in the four-dimensional structure of space-time. This point is unique to you. No one else occupies exactly the same point. Even someone sitting next to you is separated from you by a small distance in space, and because simultaneity is relative, they are also separated from you by an infinitesimal difference in time as measured across different reference frames. You are alone in your specific here and now, experiencing a present moment that belongs only to you. This isolation is not metaphorical. It is a fundamental consequence of how space-time is structured. Your present moment extends outward from your current position, defining a surface of simultaneity that includes all events you consider to be happening at the same time as your current instant. But this surface is not universal. It is specific to your reference frame, to your velocity, to your position in gravitational fields. Someone moving at a different velocity defines a different surface. Someone in a different gravitational field defines yet another surface. Every observer carves out their own present from the fabric of space-time, and these presents do not align except approximately and locally. The closest you can come to sharing a present with someone else is to be at rest relative to them, and at the same gravitational potential. In that case, your definitions of simultaneity will match almost perfectly over small distances. You and someone standing next to you on Earth's surface, both stationary relative to the ground, will agree about what is happening right now in your immediate vicinity to within nanoseconds. This agreement is so close that for all practical purposes you can treat it as perfect. You can coordinate actions, have conversations, interact in real time. The isolation is still there at a fundamental level, but it is buried beneath layers of approximation that make it irrelevant for everyday life. But move apart or move relative to each other, or sit at different elevations and the isolation begins to emerge. It remains small for human-scale separations, but it is measurable with precise instruments. Atomic clocks at different elevations tick at different rates, accumulating different amounts of time. Astronauts in orbit age differently than people on the ground. Particles moving at high speeds experience time at different rates than stationary particles. Each observer is following their own path through space-time, accumulating their own proper time, experiencing their own unique history. The paths can run parallel for a while, staying close enough that the differences are negligible, but they never truly merge. Each path is distinct. Now extend this to cosmic scales. Consider an observer in a distant galaxy, billions of light years away. They are experiencing their own present moment right now, just as you are experiencing yours. But their present is not your present. The events they consider to be happening simultaneously with their current moment are events that you would place either deep in the past or far in the future of that location, depending on your relative velocity. And the events you consider to be happening simultaneously across the universe are events they would assign to completely different times. Your two presents do not overlap except in the region of space-time that is causally connected to both of you, the events that lie in both of your past light cones. Everything else is separated by definitions of simultaneity that do not align. This observer in the distant galaxy cannot know what is happening on Earth right now according to your definition of right now. The information has not reached them yet. It will take billions of years for light to carry news of your current moment to their location. By the time they receive it, the information will be ancient history, a snapshot of a moment billions of years in their past, and you cannot know what is happening in their galaxy right now according to your definition of right now either. You can only see their past, the light that left their galaxy billions of years ago and is just now reaching your eyes. Your present and their present are separated by vast gulfs of space and time, and there is no way to bridge that separation. You're isolated from them, and they are isolated from you, each experiencing your own timeline, each unable to access the other's current moment. This isolation is not caused by technological limitations or by the difficulty of travelling vast distances. It is caused by the structure of space-time itself. The speed of light is finite. Information cannot travel faster than light. Simultaneity is relative. These are not problems to be solved. They are fundamental features of the universe, and they mean that every observer is fundamentally alone in their present moment, separated from all other present moments by the impossibility of instantaneous communication or travel. Even causality does not eliminate this isolation. You can send a signal to the distant galaxy, and they can receive it, but the signal takes billions of years to arrive. By the time it arrives, you have aged by billions of years, and so has everything in the universe. The message you sent is no longer relevant to your current situation. It is a relic of your past received in their future, connecting two moments that are no longer contemporaneous. You can establish causal connections across vast distances, but you cannot establish simultaneity. You cannot create a shared present. The universe does not permit it. And yet you're not isolated in all ways. You share a past with other observers. Everyone in your past light cone, everyone from whom light has had time to reach you, shares a causal history with you. Events in their past could have influenced events in your past. Information from their timeline could have reached your timeline. You are connected through the web of causality that links all events within each other's light cones. This web grows larger as time passes. Your past light cone expands, encompassing more and more of the universe's history. Eventually, if the universe lasts long enough, your past light cone will include the entire observable universe. You will be causally connected to everything that is observable, even if you are not simultaneous with any of it. But the future remains uncertain. Your future light cone, the region of space-time that you can potentially influence by sending signals, also expands as time passes. But you do not know what lies within it. You do not know what the universe will look like billions of years from now when your signals reach distant galaxies. You can predict based on physical laws, but you cannot observe. The future is hidden from you just as surely as the present of distant locations is hidden. You can influence it, but you cannot see it. You're confined to observing the past and experiencing the present, unable to access the future or the distant present, isolated in your own narrow slice of space-time. This isolation is shared by every observer in the universe. Everyone is alone in their present moment. Everyone is confined to their own light cone. Everyone is observing the past of distant objects and experiencing their own local now. The universe is not a single coherent stage where events unfold in a shared timeline. It is a collection of overlapping, observer-dependent timelines, each one describing reality from a particular perspective, each one equally valid, none of them universal. And the observers who experience these timelines are fundamentally separated from each other, unable to synchronize their presence, unable to share the same moment, each one navigating their own path through the four-dimensional structure of space-time. What this means is that the universe is lonelier than it appears. When you look at the night sky and see billions of stars and galaxies, you're seeing a vast cosmic community, but you're not seeing them as they are now. You're seeing them as they were, and they, if they are looking back at you, are seeing you as you were, not as you are. The present you are experiencing is yours alone. It is not shared with the stars, it is not shared with distant galaxies, it is not even perfectly shared with the person sitting next to you, though the difference is so small as to be meaningless. You are isolated in your moment, experiencing time at your own rate, defining simultaneity in your own way, travelling your own unique path through space-time. And yet this isolation is also a form of freedom. Because there is no universal present, there is no universal now that you are failing to access. Because simultaneity is relative, there is no absolute truth about what is happening elsewhere that you're missing. Your present is as valid as anyone else's present. Your timeline is as real as anyone else's timeline. You're not observing a diminished or incomplete version of reality. You're observing reality exactly as it is from your perspective, which is the only perspective you can ever have. The universe does not privilege any observer's viewpoint. It does not declare one reference frame more correct than another. It treats all observers equally, giving each one their own valid description of space-time, their own valid present, their own valid experience of time. You are alone in your moment, but everyone else is alone in theirs. The isolation is universal. It is shared by every observer in the cosmos, and in that sense, you are not alone at all. You are part of a universe where every observer experiences their own unique present, where every timeline is equally real, where every perspective is equally valid. You are isolated, but you are isolated in the same way that everyone else is isolated, and that shared condition of isolation, that universal experience of experiencing time from a singular perspective, is something that connects you to every other observer in the universe. You are alone together, each in your own moment, each travelling your own path, each experiencing time differently, but all experiencing it nonetheless, and that is what it means to exist in space-time. Time is a word you have known your entire life. You learned it as a child, you have used it countless times, you have scheduled your days by it, measured your life in it, felt it pass. It seemed like the simplest, most fundamental aspect of reality. A second was a second. An hour was an hour. Time moved forward at a constant rate, the same for everyone, everywhere. It was the one thing in the universe that never changed. But now you know that this understanding was incomplete. Time does not flow at a constant rate. It bends in response to motion. It stretches in response to gravity. It runs faster at higher elevations and slower at higher velocities. It passes differently for twins who take different paths through space-time. It dilates near black holes until it stops completely at the event horizon. It fragments across the universe into countless observer-dependent timelines that do not align, that cannot be synchronized, that belong to individual observers experiencing their own unique presence. This is not an abstract theoretical detail. This is measured reality. Atomic clocks confirm it. Particle accelerators demonstrate it. GPS satellites depend on it. Cosmic rays prove it. Astronauts live it. The evidence is overwhelming, consistent, and reproducible. Time is relative. It always has been. You simply never notice because the effects are too small at human scales, too subtle for biological senses to detect, too deeply buried beneath the approximations that make everyday life possible. What you thought was a universal river carrying everyone forward together is actually a flexible fabric that warps and curves and stretches differently for every observer. Your time is your own. It belongs to your path through space-time, to your velocity, to your position in gravitational fields. Someone moving at a different speed experiences time at a different rate. Someone at a different elevation ages at a different pace. Someone far away defines simultaneity differently than you do. Every observer carves their own timeline out of the four-dimensional structure of space-time, and these timelines are all equally real, all equally valid, none of them universal. You're smaller than you thought, not in physical size, but in temporal scope. Your present moment is not shared with the distant universe. It is local, personal, confined to the region where light travel times are negligible, and where your reference frame approximately matches those of nearby observers. Beyond that region, the present fragments into incompatible definitions that depend on velocity and perspective. You cannot know what is happening right now on the other side of the galaxy, because right now does not have a universal meaning. You can only know what happened there in the past, what you observe through light that has taken years or centuries or millennia to reach you. And yet you are also larger than you thought, because you understand this, because you can grasp, even if imperfectly, that time is not what it seems, because you can accept that your intuition is wrong, that your direct experience is incomplete, that the universe operates according to principles that exceed human perception. This understanding does not come naturally. It contradicts every instinct you have about how reality works, but it is accessible through reason, through mathematics, through careful observation and measurement. You can know truths about the universe that your senses cannot perceive. You can comprehend structures that your brain was not designed to comprehend. And in that comprehension, you touch something beyond yourself. Time will continue to feel like it flows. Your subjective experience of moments passing will not change. You will still schedule meetings, set alarms, measure durations, and age at the rate determined by your path through space-time. The universe will not feel different because you understand it better. But the meaning will have changed. When you check the time on your phone, you will know that the satellites providing your location are experiencing time differently than you are. When you look at distant stars, you will know that you are seeing their past, not their present. When you stand next to someone, you will know that your present moment is not quite their present moment, even though the difference is too small to measure without atomic clocks. You will know that you are alone in your timeline, experiencing your own unique sequence of moments, aging at your own rate, defining your own present. And you will know that this isolation is shared by everyone else in the universe, that every observer is equally alone, equally confined to their own perspective, equally unable to access a universal now that does not exist. The isolation is not a failure, it is the structure of reality, and understanding that structure is as close as you can come to seeing the universe as it truly is. Time is flexible, time is relative, time is yours, and that is all it has ever been.